Right, can I just check, can you see on your screens the Word document I've just put up? It says fixed pitch propeller. Can you see that okay? Yeah, so it's basically what it is. I think I sent out to Sanjeev to give to you as well. It's the difference between a fixed pitch propeller and the constant speed propeller, okay? All we're doing here, just a quick reference, so hopefully Sanjeev has printed this out for you. So just to recap, so your forward to airspeed and your RPM, remember your blade angle between the angle of rotation, direction of rotation and the chord line, okay? Your angle of attack is between the chord line and the relative airflow, okay? And then your helix angle, all right, towards your rotation. So what it's got there, it's got a few examples, so hopefully you can print that one out for you. So if either forward speed increases or decreases, etc., it's just a quick reference, so you can use it to revise as well. So in that case, got forward speed increases, or like in a dive, the angle of attack will decrease. Again, if forward speed decreases in a climb, the angle of attack will increase. And if RPM is increased and has more fuel, then the angle of attack will also increase. Okay, so you've got two sets there to do with forward speed, either increasing or decreasing, and you've got two at the bottom here with the RPM is increasing or decreasing and effective for your angle of attack. So it's a good reference one for revision. And pretty much the same for your constant speed one as well, okay? It's very, very much similar to what you've got there, all right? And again, reference to forward speed and whatever's going on there. The only thing that changes, we've got under speed condition, on speed condition, and over speed conditions. The blade angle must be reduced, etc., or increase appropriately. So if you get these printed out or emailed to you, you can use them for quick revision. Okay, okay. So if you've got them already, fantastic. Has anybody not got that? Have you all got them?
No.
You've not got them. I did send them to Sanjeev. I'll send it to him again, just in case. Or if you can see that on your screen top, you can take a screenshot. If you can see that already, as a quick reference. And then once you've all got a screenshot, I'll move up to the previous one. Everybody got a screenshot? I might change it down a bit. Oops. And there's the top one. There's a screenshot there as well if you want. I'll email Sanjeev just to see if he's got them. In fact, I'll just check it now while we're waiting. I'll just send them that again. Prepare the fact sheet. Okay, I'll double check it's the right one. Yeah, that's the right one. Okay. Send that. Okay, I've sent that to Sanjeev. Hopefully we can pass it on to you in case you didn't get a screenshot. Okay, but it's a good little quick revision one. It shows the diagram and it shows you some examples. Okay, you can highlight those as well, help you for your revision. Okay, it's nothing too bad there. Let's save that. It's not T-Bake, don't worry. We're still here. Okay. So, right, what we'll do, we'll just go back away in the book until I find some more items that might interest you. And we'll just check any other parts that I think may be of interest for you. Okay. All right, so going back away, we finished off some of the installation parts. If you're fitting the front cone and it's bottoming out, so the front cone bottom is correct by using or doing what? And what is the gap thickness? So that when you're putting the cones in, the front cone, it hits the flange, there's a bit of a gap left. How can we sort that gap out? And what do we do?
What?
Not that one, not the front one.
1 by 8 inch.
Yeah, you can add shims or spacers behind the rear cone, and that can push the whole hub assembly up the way, which will take up the gap. Okay. The shims of no more than 1/8 of an inch. Okay, behind the rear cone.
Page number, sir.
Page 130. All I'm doing is going to go back away through the book until we get back to day one. So page 130, the diagram there is the 4th paragraph down from where it says front cone bottoming. Basically, when you put the sub-assembly together, you tighten it up and you find a gap between the front cone and the actual hub assembly. We use a spacer shims of no more than 1/8 thickness behind the rear cone. Because if we put too many shims up there, that'll put too much pressure on the cone. Yes, it will go tight, but potentially it's going to put more stress on the hub. So no more than 1/8, just to take up that. And back on page 129, the rear cone, again, if that's not fitting properly, then we sand it down. Okay, we sand the front face down. That will allow the gap to come in. Again, up to only take about 1/16 of an inch, because this should pretty much fit, but just there could be a slight change in maybe the manufacturers produced a cone. It's a slight different tolerance. Okay, so 1/16 of an inch, not a lot at all. And you use a surface plate and a fine sanding paper, and just do a little bit of a time, check it, measure it, and check again. Okay. What are the front and rear cones made from? What's the front cone made from normally?
Steel and brass.
Yeah, steel for the front. Yeah, brass for rear. Good. And on page 124, when you're doing your shock load, or commonly known as a run-out check, we add a weight to the front of the shaft because the propeller's been taken off, and we take a reading with a DTI. Then what do we do with the reading? Do we half or double it? Yeah, half it. Now, the reason you're doing the half is because you're taking the load, or there's no gap. When you put a load on the tip of the shaft, you're pushing the shaft onto the bearing. Yeah, so there will be a little gap above it. So that gap is taking account the bottom gap and the top gap altogether. So by getting an average, obviously we just half that gap once you get a reading. Okay. Remember, rotate it 360 degrees, get a full. And you can do it a couple of times. Do it a couple of times to get an average reading. Who's this? Okay. When you're using glues or cement on your shoes for the anti-icing, the de-icing, cement should be allowed sufficient time to cure. What's the typical time and temperature for curing cement?
Hour 20.
Yeah, good. 20 degrees, good. Okay, good. Before fitting a new overshoe, the bonding area of the blade should be masked off, all trace old cement and primer removed from the area by working with stuff brush. And what type of cleaning agent would you use? It's quite nasty stuff, but it does the job really well. What's the 3 letters for it? Specified cleaning agent. Normally, remember the type of cleaning agent?
Soft caravan.
There's 3 letters.
What is the question?
PVC.
Yeah, what was the type of cleaning agent that actually gets rid of any gunk and
MEK.
MEK, yeah. MEK. It's quite potent stuff. So if you are going to use MEK, make sure you're going to identify the area, CPE filters. That's on page 121, about the fifth paragraph down. Okay. Very good. What type of cloth do you tend to use for cleaning anything? What's the name of the type of cloth?
Lint-free cloth.
Lint-free cloth, yeah. Anti-static, good. Okay. Lint-free cloth, yeah. If we're doing some repairs to the blade, we found a bit of damage to typical leading and trailing edges. Like that. The maximum length of the blade must not exceed how many inches?
1 inch per.
No. No. A little bit more. The typical leading and trailing edges, we get a depth, we can work it 10 times the depth.
7 inches. 7 inches.
7 inches, yeah. That's on page 116, the top of 116. If you're finishing a blend on a typical camber face, after removing visible damage, what must you also remove extra? Get past. You see the damage, you go down to the damage, and then how much more do you remove after the damage? Very small amount.
30 times.
That's the depth over distance, but how about the depth? So you file it down to where the damage is, but then we go a little bit past that, right? Remember how much that was?
0.00102 inch.
Yeah, basically 2/1000 of an inch. 2/1000 of an inch. Okay. Good. What is the limited rework depth of the face of a camber?
10 times.
Well, that's the overall length, yeah, the actual depth. What's the rework depth? So we can go down to how much? If I said to you 10 thou, 20 thou, 40. 40,000 inch, good. And the reduction of the blade thickness must not exceed what percentage?
25%.
Yeah, that's what you said it.
In which page number it belongs, sir?
The reduction of the blade thickness must not
1.5.
25%, yeah, basically a quarter of the blade. Any more than a quarter of the blade's thickness, well, that's going to be quite weak, isn't it? So no more than 25%. And the damage area must be blended out in all directions, at least how many times the depth of indentation? Yeah, 30 times, yeah, good. And also, for a camber area, we saw on the leading and trailing edge is no more than 7 inches, but for a camber one, it's no more than how many inches?
Excuse me?
No, not 0.4, just 4 inches. 4 inches maximum. So we can go 30 times the depth of the blend, that's fine, but that must not exceed more than 4 inches in total, okay? That's on the camber part of the blade, all right? Okay, good. That's fine, yeah.
Excuse me?
Yeah.
At the end, if you tell the page number, it will be very fine for us.
Okay, yeah, sure. That was on page 115. I'll make sure it's the same one. Just double check it's the same page number, because I've got an slightly older model, but it should be the same number. Page 115, the top should say typical face and camber repairs. Is that the same page? Yeah, typical face and camber repairs. That's where it should start. Is that the same one?
Yeah.
Okay, good, because I've got a slightly older version, but it should be the same. It just updated the front cover, that's all I've done. So page 115, typical face and camber pairs. And the first 2-3 paragraphs there, you've got 40 thou, 25%, 30 times, and 4 inch in direction. And then over the page, that is for your 116 for the typical leading and trailing edge repairs, okay? So all I'm doing, I'm going back away from what we've done and see where we've got from there. All right. Okay, page 112, typical composite blade repair. Who can do a major repair on a composite blade? Yeah, only manufacturer. Yeah, let's go back to manufacturer. You can do a minor repair. And how can you test a composite or carbon type or Kevlar blade for damage? Apart from visible, what you see, what are you also checking for? Delamination. So what's the simple technique for checking delamination? Yeah, get a coin, just
Coin.
tap along, nice and gentle, and you hear the difference in tone. And that it should be the same tone all the way, but if you hear a slight difference in tone, then that's potentially it's starting to delaminate. Okay, good. Okay, 111, overspeeding. If the engine, or the propeller, sorry, overspeeds up to 115%, what checks should you carry out? So up to 115%. Or do you need to check anything? No, not in this one, no. This is the first, you're allowed up to a certain amount of percentage overspeed. It's probably worth checking the tracking at least, because if you've got an overspeed, that's going to provide more thrust. The blade's going to try and bend even more forward at 115%. Normally you don't need anything, also depends how long it was overspeeding for. If it's just a brief moment, it's usually okay. But as a precaution, you would check the tracking, okay? Do the tracking check on it. So that's up to 150%. From 115% to 130%, what would you check now? You've actually just said it. Yeah, just do your NDT, do a dye penetrant, cover it, make sure there's no cracking because it's overstressed it a little bit. Blade bearings, etc., crack tested. Okay, hub and counterweights you've inspected for cracks as well. And then the final one is 130%. So say the propeller goes over 130%, what would you do?
DPA.
Yeah, just send it back and give the pilot a slap in the back of his head for being naughty. Okay, he's been too fast. Now, it could be a mechanical problem. It's not always the pilot's fault. Most pilots are good, but you get occasional pilots. They think they're in Top Gun. Okay, so yeah, if it overspeeds 130%, send it, take it off, and back to manufacturer. Good, good, good. You've got some good ones in there, that's fine. Okay, again, when looking for damage, scratches, cuts, scoring, etc., they are all things that can potentially lead to cracking of a propeller blade. So yeah, take your time when you're inspecting the blades. If in doubt, get the NDT out, okay? Get non-destructive testing. Go and do a dye penetrant and check it, because sometimes it can just look a little hair or it could just look like a little bit of dirt. But again, if it doesn't wipe off, that's potentially a bit of potential cracking. So if you are in doubt, raise a job card and go and get NDT, obviously, yeah. All right, so nothing too bad on there, hopefully. In which chapter of the propeller maintenance manual would you find details of servicing damaged blades? What would be the chapter number?
6110.
61.
Yeah. Yeah. Again, once you're obviously once they're authorised and certified, you can actually go repair them, minor rectifications. How much force during normal operation, central figure force of tonnage would the propeller experience on average? The blade itself might only weigh maybe what, 10 kilograms or something like that. How much extra force does that apply when it actually starts spinning? How many tons on average? What do you think?
10 to 25.
Yeah, 10 to 25 tons. Good. So going back away.
Page number, sir.
It's 101.
101.
Then we go back away where you might have potential, you might have a slight over speed, so we'll check the tracking. So like tell the round once, we line off one blade, you spin it round and then mark it off on a bit of board, and the track should be within how much of an inch?
1/6.
Yeah, 1/60 of an inch. Page 100. Okay. Okay. And what is the height? So where the tip comes round to the board, what's the gap between the tip of the blade and the board where you mark it on? What's the board gap? You don't want it too big. What would it be? Yeah, quarter of an inch. Yeah. You want enough gap so you can spin the propeller around, not touch the board, but not too big because that'll give you a bigger error. Yeah. So a quarter of an inch maximum. So as you spin around, it will clear the board, but enough to get an accurate type measurement. Good. When is dynamic balancing carried out? So when would you carry out dynamic balancing? Would it be off the aircraft or on the aircraft? Yeah, it's the only time you can do it when you attach the engine and you go and spin it up. Now remember, dynamic balancing, it could be affected by engine mounts, it could be affected by doors vibrating, so be aware, once you can isolate those potential faults, then you can do dynamic balancing. All right. The static balancing is carried out using what? How do we carry? Let's say again. Knife edge, yeah, knife edges, yeah, sorry. Yeah, page 96, 97, you'll get two knife edges. They'll use a mandrel, an arbor, to go through the center, and then those will be placed onto the knife, and then make sure the propeller is free to rotate all the way around. They'll do a vertical check, and they do a horizontal check as well, okay? So it's just two types, just static balancing and dynamic balancing, all right? Okay.
What is the question in dynamic balancing, sir?
The what, sorry?
What is the question you asked at the dynamic balancing?
Oh, the dynamic balancing is when would you carry out dynamic balancing? Would it be on the aircraft or off the aircraft? So it's just, you can only do it on the aircraft, really, yeah? Because you need to spin it up. So
placed on the aircraft.
Yeah. So static balance is off the aircraft on the knife edges, and you'll be checking for static balance. Which axis does the static balance go through? Is it the axis of rotation or the plane of rotation for static balance? Yeah, that's right. So it's pretty much in line with the engine. Yeah. So we're spinning the propeller around the axis of rotation. So we're hoping that when it sits there horizontal, it should stay where it is, and if it's vertical, it should stay where it is as well. Okay. The dynamic balance is with the plane of rotation. In other words, blade tip to blade tip, or perpendicular to your engine. That makes sense. They might mix the words up. For a question that may ask you what is static, what is the axis of rotation referring to balance? That'll be static balance. Okay, they might just, it depends how the word the question, depends on the word question. But the three main types are dynamic, static, and aerodynamic imbalance. Okay. Okay, going back a way, we're looking at de-icing systems, the fast and slow cycle. If I've switched the heating system onto a fast cycle, what is the conditions I'm flying through? High temp and high or low water concentration. That's what everybody thinks. It's high water concentration. Just think high temperature, high water. Yeah. Because it's a high temperature, you think, well, we shouldn't be getting icing, but because you've got fast moving air over the propeller, that means reduced pressure, reduced temperature. So with a lot of moisture in there, that could potentially ice up as well. Okay, so a fast cycle is required for when it's high temperatures, but also high water content. Okay.
Yeah, humidity.
So high humidity. It might be worded as high humidity. So the answers in the question could be high air temperatures, high water concentration, or high temperature, low water concentration, or it might say low temperature or something daft, some crazy sort of answers. So make sure it's just think high temperature, high water, or a lot of water concentration. Okay. And the slow cycle, well, it's cold, so there's a good chance it's going to freeze up. So cold and definitely water, yeah, good chance it could freeze up. We'll have the heating system on longer, so it will stay on longer, hence the slow speed cycle. Okay. And there's always a question on either one of those. Again, whichever one you get will determine on Sunday. So your fast cycle and your slow cycle.
In high, you can also say high moisture. In high temperature.
Yeah, humidity also.
Yeah, high humidity. Yeah, it depends on which way they word. They might say high humidity, which means a high water concentration. Okay, they might say high water concentration, or they might say high humidity. So the answers might give you is high temperature, high humidity, or high temperature, low humidity. Well, it's a high humidity. Where there is greatest amount of water, and even in a high temperature, there's still potential for icing to happen. And the same for when you do module 15. When you ground run an engine, when you have your engine guard on the intake, there's potential, even with a warm temperature, with high humidity or high water content, you can have ice formation on the intake of the engine as well. And we'll speak about that next week, or later on next week in module 15. So just think high, high temp, high water, or lots of water. Okay, let's see, that one's okay there. Okay, looking at fluid ice elimination systems, looking at page 82, 83. The pressure developed by the pump is no more than about approximately how much PSI? Is it 10 PSI? Yeah, 10 PSI, yeah. I was going to give some options there. Okay, good. And the check valve opens at what PSI? 3 to 5, good. Wait my lips. And the pump speed is controlled in the cockpit by what? What controls the pump speed on that control rheostat? Yeah, just varies the amount of voltage to the pump. Okay, that's all it does. And what's the purpose of the check valve in the system? What does it prevent?
To prevent siphoning.
Yeah, it prevents the siphoning. Okay, draining it, and especially at evaporating as well. What is the most common type of fluid used for fluid de-icing?
It's
Isopropyl alcohol. It's low cost, but however, what's it also not good at, or what is it not very good for? Or what's its disadvantage?
high flammability.
Yeah, high flammability, definitely, yeah. Okay, another type is the phosphate compounds, but it's dearer and safer, but it's dearer as well. Okay. What is active synchrophasing? And that's on page 80. Active synchrophasing. Yeah. So we can add more systems into the cockpit. We can have speakers and microphones, and that will sense a vibration or listen to a vibration. It will automatically do it. But what's the disadvantage of that? Exactly. High cost, more things to try and fix, and weight. Yeah, too much weight as well. So weight
Page
pencil.
number, sir.
That was page 80. Page 80.
80.
But your typical system, you have your synchrophaser panel. Okay, you can have it off, sync, or phase. What is synchronization?
Yeah.
Yeah, good. So we'll have a master engine, set the RPM for that, and then we'll match the other one. And then at the same time, we can set the angle where the blade starts and stops from. We can retard it a little bit or advance it a little bit to make it slightly out of phase. Good. Synchrophase angles in some aircraft may not be properly optimized. Now, within what sort of angle? What sort of degrees? That's page 76. 5 degrees, yeah. What do we fit at the same blade root of every propeller so we can get a signal to the system? What's the component called? Pulse channel, yeah, we fit it in the same position on every number 1 blade of each engine, yeah, so it's the same position. Good, we've done that one, phasing, yeah.
Can't show something.
खोइ दालजी के बनायो भने सब मैं
On a twin engine aircraft, which engine is usually the master?
Is engine 1 left?
Yeah, left-hand
Left
side,
engine.
yeah. Good. Okay, going back away, page 72. Typical gas turbine engine blade frequencies range from how many hertz to how many hertz?
60 to 120.
Yeah. Noise levels can exceed how much decibels?
100.
100, yeah. Good. Okay, that's fine there. Leave those ones. What do we call? Well, no, let's start with easy one. What is FADEC? What does FADEC stand for?
Fully authority.
Full authority digital engine control.
Good. Yeah. Basically the brain. Full authority digital engine control. Yeah, it's the computer brain takes away the mechanical control. Yeah. Okay. Okay. In propeller overspeed on page 66, if the FADEC was to fail, what takes over?
Governor, overspeed governor.
Overspeed, yeah. And the same as the CSU. If the CSU fails, the PCU fails, the overspeed governor will be preset. Do you remember the RPM and the percentage figures?
2080 and 140.
080 RPM.
Yeah, 2080 RPM or 104% NF. What does NF stand for? Speed of the free turbine, yeah, good. We don't want that to happen. All is good.
Do you have to remember this?
Yes and no, I don't know. It's again, I've not seen the questions. It'd be worth highlighting. If you can remember that, then good. If you remember the percentage, maybe you at least remember one of them, the 104% NF for free turbine, then possibly, yeah. The only one there is you have a test switch that just pretends that it's working. Okay. Yeah, maybe remember 104%, just in case. At least remember one of the two. Hopefully it'll let you know what the answer is. What do we add to shafts and turboprop aircraft to stop the windmilling when on the ground? Propeller brake, yeah. Basically, that's like a normal brake on a car, yeah. And it can only be activated when a certain speed. But however, yeah. And what do we have fitted to the brake connection in case we overheat it?
High pressure shut-off valve.
No, that's the HP cock. What's on the brake system that will blow if it overheats? We'll have the brake. Yeah, fusible plug. Yeah.
Fuse plug.
What they'll do, that'll release the pressure, and allow it to spin, so we don't get a fire. And they've got the same system on many aircraft undercarriage wheels as well. Have a fusible plug, which will be part of your checks when you're doing service on an aircraft, to check the fusible plugs on your main wheels haven't also blown as well. Because that'd be embarrassing. You come and land and you press the brakes and you've no pressure. But the same
Page
happens
number कति?
on the pressure. That's
64.
on page 64. 64, yeah.
That's all.
Okay. Let's think first. That one's okay. The reverse thrust ones from page 60, 61 is pretty straightforward, I think. There's nothing much there. The only things you might want to remember, page 60, selection and operation of thrust reverse inhibited, which is fail-safe, until the following criteria are met.
Yeah.
Now, you can't select it until you've got the 4 options there. Page 60 is engine power minimum, the idle, the aircraft airspeed, and attitude is correct. In other words, you're on the ground, not in the air, and your forward speed is at a certain speed. Weight on wheels, in other words, your weight on your wow switch, your weight on wheel switch, and your flight ground flying pitch stops are removed. So it might be worth highlighting those on page 60 if you haven't done so already. Requirements for thrust reverse. Okay, that's fine there. Let's see if there's anything I can highlight that one for you. Let's see. Okay, yeah, page 54, where we're on about feathering a double acting propeller. The very last paragraph on there, worth noting as well. When the blade's in fully fed position, oil pressure builds up in the delivery line, which operates a pressure-operated cutout switch, or POCOS. As it's called, Hocus Pocus. The POCOS switch, which de-energizes the feathering pump. So say they give you a question, what switch would de-energize a feathering pump? It'd be the POCUS switch, the pressure-operated cutout switch. That's probably worth highlighting.
Well, in which just now, sir?
54, 54.
Page
54.
54, last paragraph.
Very last paragraph, yeah.
Okay.
Just highlight that one. It's the POCUS switch. Just think Hocus Pocus. All right, that's forward there. And then page 51, feathering a single acting propeller. And I've got a note there, the third paragraph. On light aircraft, on light aircraft, how do you unfeather a propeller on a light aircraft? What component is activated?
Accumulator.
Yeah, accumulator stores energy. Large aircraft, you'll have a pump, because the pump's a bit heavier. On light aircraft, we don't really want something that heavy, but we will use an accumulator. Okay, good.
कति पेज नम्बर भन्यो तर
51.
Okay, on page 50, what would be the two effects of a propeller if an engine failed in flight and it did not go to a fair position? What could potentially happen? Two things.
Increase the drag.
Yeah, increase the drag.
Damage the engine.
Yeah, because we could start spinning because of the forward airflow hitting the propeller, spinning around, and that propeller spinning around acts as a big windbreak, so it could actually pull the aircraft round to one side, which is obviously quite dangerous. What type of aircraft would not have a feathering system? Camera's open.
single engine.
Single engine, yeah.
Single engine, yeah, because if an engine fails, at least if you've got in a sort of fine position, that can slow the aircraft down as it's coming to potentially crash land, or hopefully get some control. But we've got in a fair position, well, there's no resistance from the blade, so the aircraft's going to come a lot faster, basically like a very heavy glider. So by not having a fair system on a single engine, you can use the propeller as an air brake, and it helps. It just gives the pilot a bit more time to try and figure out some sort of a safe landing somewhere. Trying to remember where I saw that. It is in the book. I can't remember where it is now. Where I put it now. fine. Okay, page 48, what does the Planck formula refer to? Horsepower, yeah. So what does P stand for?
Mean effective pressure,
Yeah. L,
length of stroke,
yeah, so that's the stroke of the piston, the actual bit goes up and down. A,
area of piston,
yeah. N,
number of stroke per minute,
yeah, and K.
number of cylinder.
Good man, good man. The only table I might get to just keep an eye on is page 49. And you've got the 4 settings there. It's worth reading over it and understanding what's going on there. So what you can do is we've got the throttle settings, put a line underneath the throttle ones and revise those two. And then below that, you can revise the propeller settings. So you've got throttle setting, throttle set and propeller control increased. It tells you what's happening to horsepower and propeller pitch as well. So maybe worth just highlighting those ones. So the first two is to do with the throttle setting and either propeller control increased or propeller control decreased, and that tells you what happens to the position of the propeller. Then you've got a propeller control set for the bottom two, and either throttle increased or throttle decreased. And again, it tells you propeller to coarse or fine. Okay, so it might be worth keeping an eye on those ones. Just in case, just in case. Okay, give me some examples of flight deck instrumentation you might see in the cockpit on page 47.
Engine RPM, engine
Yeah.
power,
Yeah,
engine manifold pressure, vibration range,
Beta range.
fuel
Yeah.
flow, beta range.
there's quite a few bits there, yeah, good. Okay. The power lever has generally 4 positions, which are
Reverse, ground idle, flight
Yeah.
idle.
max, yeah, and the condition lever, also known as the other lever, is also known as the speed lever, I should say. 3 positions.
Low and high RPM.
Good. Okay, doke. And what do we call that range in thrust reverse when it goes below ground idle? What was the name of that range?
Below what?
Better range.
So we bring the lever back to ground idle, then we go below ground idle. What was the name of that range below ground idle?
Reverse.
It is in reverse, but there's another name for it.
Better range.
Say again?
No. Beta range.
Yeah, that's right. Yeah,
What-
beta range. Yeah,
What range?
beta range. Again, only accessible when the aircraft's on the ground and you've got your weight on wheel switch has engaged, which allows the circuit to work. All right. Right, if we go back to page 39, it was on about the power lever positions. You've got single lever or controls from A to D and that sort of thing. That represents the full range of the power pitch control. Whether they ask you a question that I'm not too sure, because they can't show you a diagram, but they might say, what is it, position A, and when does the, probably the note on page 41, minimum constant speed is the minimum RPM selected by the PCU and allows rapid acceleration. So on page 41, it might be worth highlighting that one with reference to control. So minimum constant speed is the minimum RPM selected by the PCU and allows rapid acceleration. I think I've
Is
got all
that
those,
note person?
which is page 41, yeah.
Yeah.
It's got a note
person
yeah,
one.
just underneath the diagram. It says a note. Probably highlight that one. Okay. Sounds okay. Okay, page 35. When we're looking at flight fine pitch stop withdrawal, we'll get an indication in the cockpit. Now, if the light is on, what does that indicate about the flight fine pitch stop?
Stop withdraw.
Yeah, stop withdrawn. Yeah, so it allows the pilot to say, okay, the flight fine pitch is out of the way. I can now go into reverse thrust if need be. However, there also, if he's not selected that and the light comes on, that potentially is a potential fault within the actual mechanism. So if the light's out, the stop is locked. If the light is on, it means the stop is withdrawn. It's a warning to let them know that is out.
Stop withdrawn means it's warning.
Yeah, it's a warning to. If you look at page 34, you'll see the flight find stop on the left-hand side of the diagram. Okay, that will let you see a bit of. It's got one in the page 35 as well, but the page 34 gives a bit of diagram. Page 35. Page 35. You look at where the little red piston is on the left-hand side, and there's a little blue above it. That's your flight find pitch stop. Now, normally it's in a locked position. When you put oil pressure into the white area, that will push the little red piston back. That will allow the flight find stop to withdraw, which allow the piston to go to the fine pitch as well, sort of thing. Okay, so watch out for that. Okay, anything on that one? GFP stops. The ground fine pitch stop can only be activated or only work when the flight fine pitch stop is out of the way. So if the flight fine pitch stop lights up in the cockpit during normal flight, then potentially the ground fine, it could go really, really fine, but it doesn't need to be. Okay, shouldn't be in the normal flight fine pitch stop all the way. Only when the pilot selects for takeoff, it should be out of the way. Right, then we move on to on speed, under speed, and over speed conditions. Okay, in the single acting, sorry, we're looking at double acting. So remember, in double acting, your pilot valve, if the control slides upwards, it will direct flow of oil to the front of the piston, which will move the piston back the way, which will then coarsen the blade, which will then slow the RPM down. Okay. And likewise, underside, the slide valve will go up the way, which will direct oil to the back of the piston, which will move the piston forward, which will then fine the blade off, which will allow it to speed up. Okay, that's for a double acting one. And on condition, everything's happy, it's all okay. But for a single acting one, it does the opposite. Just to make it really confusing, it makes it a bit opposite. The underspeed, again, the flyweights will come back down. The valve will also go down. But this time, it will put the oil to the front of the piston to push it to the back to fine off the blade. And likewise, on overspeed condition, it will release the oil pressure from the front of the piston, and then the spring takes over, pushes the piston forward, which pushes it into a more coarser and even further position. So a single acting piston does the opposite from a double acting piston. Okay, just to be different. They both work, but they both do the opposite way around. That's just to make it confusing for you. Again, by simply swapping the pipes over, it could make it work the same way. But hey, I'm not the designer. That's the way they designed it. Right then. Okay, that's fine there. Back to page, let's go for page 20. We're looking at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the 12th paragraph down. I've got just a highlight there if you haven't done already. Each engine drives an alternator which supplies a three-phase alternating current to the stator windings of the appropriate contactor. The frequency, is the key word here, is proportional to engine speed. Okay, so the frequency is proportional to engine speed. So as the speed goes up, frequency increases, and likewise it slows down, frequency decreases. Right, okay. What is the basic operating principle of a geared or hydromatic type system? So what is a basic principle? What's involved? Just some basic names there. A geared or hydromatic system.
Centrifugal twisting movement.
Yeah, so we've got bevel gears, we've got propeller like that, and then we've got the gear from the twisting of the shaft. Okay, But what makes that twisting happen? What do we call the gap where the little roller sits in? What was the common name we call it? We've got a cam that rolls inside this little slot, and the slot looks like
Dogleg slot.
Dog slip.
That's it. On page 17.
Yeah, dog legs.
Dog leg, because it looks like a dog's leg, all right? Little dog's leg. So the cam, the rod stays straight. It's got a little roller on it. As it rolls in, it will push on the face of the dog leg, which will push it down. And likewise, if it's going back the way, it will push on the upper face and move the cylinder round. So we'll either rotate the cylinder one way or rotate it the other way. And as the gear is at 90 degrees, okay, it will rotate that way or that way accordingly as well. Okay, just a slightly different version. Then we've got the moving cylinder. So you can have a moving piston. So the piston inside the cylinder moves back and forward, or you can have the cylinder which moves back and forward. They both do the same job, just again, the design has been different, a different way of doing the same job, all right, on a single acting one. So moving cylinder, the coarse pitch oil would go through the center, okay, and come out the back of the piston. The fine pitch would go through the front. Page 15 and 16. All right. So you get double acting. Single acting, nice and straightforward. We just have a big spring and oil pressure at the front. Okay. How are centrifugal latch stop mechanisms released? What releases the centrifugal latch stop mechanisms?
Solenoid.
Anybody?
Prevent feathering.
Sir,
What is the question?
It'll be latch stop there, but how do we want to get that piston to move further back into position? How do we get the latch stops to move so we can actually move the piston to fully fit?
Centrifugal latch.
So we've got the centrifugal latches. So what actually moves them out of the way? Is it electrical, hydraulical, or centrifugal force?
Centrifugal force.
Hence why they solved centrifugal plates. If you look at page 13, you will see on the page, on the top of page 13, the diagram, you'll see the latch weights are holding the stop plate in position. As the centrifugal force gets faster, the weights get moved up into the little recess, which is in the green part. That allows the latch to disengage.
page number.
Page 13. Page 13. You see the diagram?
Got it.
Yeah, diagram at the top. You'll see the latches there. Okay. So just by purely centrifugal action, they spin out of the way, which allows the stop to disengage, which allows the piston to go forward into fully feather position. Okay. Go right there. Okay, going back to sort of basics with CSU, two methods are used to vary the pitch of a propeller. What are they?
Engine oil pressure and engine pitch control mechanism.
Yeah. So engine oil pressure in commercial aircraft and electrical pitch mechanism generally for light or smaller aircraft. Okay. Everyone else should be happy there. Just done that one. All good. Happy with those ones. Where would you find a PCU? What type of engine?
Turbine propeller.
Gas turbine one, yeah.
Piston.
Yes, it's the piston. Yeah.
Piston is for CSU.
Yeah, that's right. It's a pity they didn't make it PCU for piston. That'd make it easier to remember. But they've got PCU for a gas turbine instead. Okay, that's just a quick run through of book 2. We've done the questions there. So we'll just run through some of the questions in book 1. So without looking at your answers, I'll read the questions out and see you come with answers. So book 1, page 113, Common types of wood used to build a propeller are, we've got 5 types. What types of wood have we got?
It's in
Anybody
propeller
remember?
construction.
Yeah. So what type of wood do we use to make a wooden propeller?
Normally,
Beads, most common one.
What's the most common one?
Beads.
Birch. Yeah, birch.
Yeah.
Okay. And we've got mahogany. What else?
cherry
Cherry. Yeah.
and black walnut
Black walnut. And
and oak.
oh, good. Yeah.
Sir, break.
Yeah, beads is the
Okay.
most common one, so
That's
we
right.
remember only that one.
Just hopefully it's just that one. Okay, I'll pick a random question. A fixed pitch propeller during takeoff, the angle of attack will be large or small?
It will be large.
Yeah. On a fixed pitch, because it's fixed pitch, we can't change it, so it will be large initially until we get forward speed, until the angle decreases. Yeah. So eventually we can go take a long run, then it can take off higher. Yeah. Good. On a spline propeller, the hub is normally centralized on the shaft by front and rear. What? Cones, yeah, good. Some fixed pitch propellers designs have their balance adjusted by placing lead wool and balance holes near the hub and also attaching what to the side of the hub. What else can we attach to the side of the hub? We can put lead wool and balance holes, and can also attach what else to the side of the hub. Just think of a car wheel. How do you balance the wheel? Say again? No.
Counterweight.
Yeah, well, yes, not yeah, sort of. It's not quite a counterweight, but it's balance weights. Yeah, you can attach just like in a wheel in the car. Your wheel will be balanced, and we'll add or reduce or remove weights accordingly to balance the wheel out. Okay.
What is the page number, sir?
That page, just the questions. That was page
It's from
113.
113.
113. Yeah, 150.
Answer counterweight. Sir, 10-minute break.
Say again?
Yeah, 10-minute break.
Yes, sir, break,
Yeah,
sir. Tea break.
Yeah, okay. I'll tell you what, yeah, if you come back at 10:30,
10,
okay, 10, 15 break,
10, 15.
we'll just finish off there. We'll get away short.
15 break. Yeah. Okay, sir.
Right, last 10, 15 minutes, guys. I think that's all you'll need because your heads will be exploding, I think, by now. Are we surviving? Or have you all gone home? Anybody out there? Hey, hello, there he is. See, you can actually see some people. I'm not just looking at screens. Good stuff. Just think, get a break, then you have exam, and then you start all over again with me doing module 15. Hey! All good fun. Right, we're only going to finish book 1. That's as much I'll give you today once I've gone through some of these bits with you. So you both finished a little bit earlier today, so give you a little bit of, let your brains rest, okay, let you absorb all that knowledge, ready for your exam on Sunday. Did I mention you got an exam Sunday? I laugh because I don't have to do the exam, thankfully. I just have to teach you all this good gen. Hopefully it's good gen. Okay, so the last sort of 10, 15 minutes, in, if that at all, we'll just finish it off, quickly run through the book of book 1. Then that will be it. And if you have any questions for me, you please feel free to see if there's anything you want to go through. So just keep going back. We'll start on page 104 there. Just going back the way. Reversing engineering. Oh, that's money. Get you back in. So who can remember typical aluminium propeller assembly? Approximately how many steel balls and plastic
30
balls?
steel ball and 30 plastic ball.
Yeah, 30 and 30, yeah. What is specific about the weight that you attach? What's special about the weight? Can we just grab any weight, or should be what type of set? The counterweight assembly. So we can add the decreased amount of weights in the counterweight assembly, but what should we make sure that the weights are?
Counterweight assembly.
Yeah, remember, there should be a matched set. We don't just pick any random weights. There should be a matched set, okay? That's on page 104. 2 basic ways of fitting a propeller assembly to an aircraft engine is... What's the 2 basic methods? How do we fit the hub assembly to the reduction gearbox? What's the 2 basic methods?
Spline and bolted.
Yeah,
Spline
spline shaft.
Spline shaft and the voltage flange.
That's it, good. If I said I've got a tractor type engine, tractor type aircraft, is the engines at the front or the back of the
Yeah, front of the engine.
Yeah, okay, good. Nice and easy peasy.
And the pusher rear of the engine.
Yeah. Which type of engine configuration will generally have a quieter environment? You're starting to, sorry?
The pusher type.
Yeah, it's behind, it's out of the way.
Or the, yeah. Or the engine, only one engine mounted ahead.
Yeah, okay, good. I think that's all straightforward there for you guys, not too bad at all. Okay, then we move on to your angles. Is everybody happy with RPM, aircraft forward speed in relation to the blade angle? Is anybody still a bit stuck in that? Hopefully you should be okay with that now. Anybody got any problems with that one? So as the forward speed increases, the angle of attack decreases.
Steady flight is...
Yeah, anybody still a bit stuck in that one? Okay, anybody not happy with that? You're guaranteed to be asked a question on whichever configuration they give you, but it's aircraft going in a climb, aircraft going in a dive, etc. Okay, that's just Sanjeev saying thanks in case of the calendar mission. Okay, so Sanjeev got that sheet I showed you earlier about just what we've been chatting about now. So hopefully he can pass it on to yourselves, just as a quick reference for revision as well. Okay. Yeah, so all that should be all okay. Again, unless you've got any problems with that one we've covered. How many unidirectional shear webs are normally placed between the camber and the face surface in a composite blade construction? How many shear webs normally?